Good morning, everyone. I'm Alampi, and I'm here to tell you about an interdisciplinary study that Mike Fehler and I performed in the Earth Resources Laboratory. We were very interested in both the oil and gas industry and sort of the geophysics behind what they do there, and the business behind the work that people are doing, specifically as it relates to a new technology called hydraulic fracturing. And some of you might be familiar with this term, some of you might not be. So I'm going to start off the talk with some background, give you a sense of where the oil and gas industry is today, and then where we saw room for them to become perhaps more efficient. So, to tell you some background, the US energy industry has changed very rapidly since 2008. And as you'll see from throughout this presentation, at the top of the slides, I'm going to continue putting the title of this talk so that as I define terms and you become more familiar with what I'm talking about, you'll see where we're at and where I'm going. US oil production is currently at its highest level since 2008, and I'll show you a little bit of data behind that. In 1980 and through about 1986, 1988, we were at our highest levels of oil and gas production. And then it steeply declined for the following 10 to 15 years until the early 21st century when we began kind of going on the up and up, and we've seen very steep, very rapid growth in the oil and gas industry due to a new production technology called hydraulic fracturing. I'm going to refer to hydraulic fracturing as hydrofracking, fracking. All these terms are interchangeable, so if I use one time and a different one another time, don't be confused. And the US will likely be the world's largest oil producer by about 2015 due to fracking. To give you an outline of where this presentation is going, I'm going to begin with some more background, some more context for our study. Then I'll carry on to our research question and then the answer, which comes in two parts, wrapping up with some conclusions and then the opportunity for all of you to ask me some questions. So for background, you might have some questions relating back to the title of this talk, and the first might be what is hydrofracturing, and then the second might be how do operators decide where to frack? And operators just means companies. So oil and gas companies are operators in their oil and gas fields. To define hydraulic fracturing and give you a sense of how it exactly works, companies basically drill holes in the ground. That's their job. And those holes in the ground, sometimes they're vertical, they're straight up and down. Sometimes they start off vertical and then they turn horizontal. And you can see that here. I'm going to describe a little bit more about that later. But once they do that, they open holes in the casing surrounding their drill, and then they open up fractures in rock. And when they open up fractures, then all of the oil and gas is more easily able to travel through those fractures. And they put tremendous amounts of water to open up those fractures, as well as particulates, so things like sand or maybe man-made replicas of sand, and those are called proppants. And you see in the zoomed-in image on the left there, well, my left, your right, that's a zoomed-in image of tiny little pieces of sand that are keeping fractures open in rock. So that's the outline of how fracking works. And specifically in California, the area of our study, they don't use liquid water to frack, they actually use steam. So to give you a sense of how that works, they first just inject steam into a well, and this image shows you what I meant by straight up and down wells. That steam stays in the reservoir, sort of soaks there, and heats up all the oil and gas, makes it thinner, which allows it to more easily travel to the surface in the production stage, the third stage. And during then, that's when the actual oil and gas get up out of the ground and oil and gas companies make their money. So today, directional drilling, that is drilling that even if it starts out vertical, turns in a different direction. That might be actually horizontal, or it might just be a non-vertical angle. Directional drilling was a huge technological challenge, one faced mostly by the engineers who were trying to figure out how to get drills to turn sideways. And now it's economical and it works. And that's why we've seen booms in the areas like the Bakken, a huge oil field in the Dakotas. We've also seen it in Texas, where the original technologies were discovered. And even though those are the two main sources of the directional drilling technology, we found it very interesting to study California, which has a very long history of steam injection, almost 60 years now, but only just in the past 10 to 15 years has started drilling in non-vertical directions. To give you a geographic sense of the part of California we're talking about, you can see these stars, which are clustered around the Bakersfield area. That's where the drilling has happened for about 60 years, and then they frack those wells. And so this map was provided by the state of California government. They give us all sorts of helpful data that also made our study a lot easier, because it was difficult to find data given the competitive nature of oil and gas and the fact that they don't often want to share as much data as we might like them to. So here we're able to get a really clear sense of exactly where people are drilling, and then to chart that over time, study that in more depth. And this is called California District 4. That's not a term to get caught up in. That's just that's a reflection of where certain counties in California are. So they cluster a few counties into each district. Now, in California, specifically surrounding the Bakersfield area, there are 7 main operators that frack, 7 main operators that use this technology. And I'm going to go through them chronologically. So you'll see that this data table is going to kind of fall out onto the slide. The left-hand side is the operator name. The right-hand side is when they first started to both frack and to drill in non-vertical directions, directionally. So the first mover, the first company to get involved in this in California was ENERGY. And that name might not sound very familiar, but they are actually a subsidiary that's partly owned by Shell and partly owned by ExxonMobil. So they are sort of a composite of multiple large oil and gas companies, but they operate just in California. And then it took a whole 7 years for another company to come into California and frack as well, and that was Vintage Production, not as familiar a company, much smaller. They only operate in California as well, but they don't have any sort of owner that's big like Shell or Exxon. The next 3 companies might be more familiar. The first 2 are ExxonMobil and Chevron. They both showed up around 2010, 2011, and they're super majors. So that means that they're international oil companies. They have billions and billions of dollars of revenue every year, and a whole lot more wells and research than the average oil and gas company might have. And Occidental of Elk Hills is sort of the largest small company that you'll see. So small is still enormous, but they're smaller than Chevron and Exxon. Finally, these are 2 names that probably aren't familiar to any of you because they're family-owned or very, very small, and again, they just operate in California. These 2 were interesting because Brightburn Operating just began to frack in California in about 2013, and McPherson, we suspect, also began in about 2013, but we can't quite be sure because they don't provide the dates of their wells being drilled. So that just tells you sort of the competitive landscape of who there is in California. And later, when I show you our research methods, you'll see that we were comparing across these companies in order to see just how effective microseismic monitoring was when some companies used it and some companies did not. Now, these companies use different methods to decide where they're going to frack, and they vary in sophistication. So the engineers are a little bit less sophisticated. They like to make assumptions, basically saying that there's this body of homogeneous rock and it all has the same properties and it fractures the same way. And geophysicists and geologists know that that's not quite the case. There are more sophisticated methods that you can use to understand what rock looks like under the ground and how it fractures, and therefore how much fluid you need to pump into it in order to open up those fractures. So geophysicists use things such as microseismic monitoring and tilt meters, which are ways to understand how rock fractures. I'll go into more detail about that, but microseismic monitoring wound up being the method that people use in California. Tilt meters wound up not being as significant, so I'm not going to talk very much about it. So we're going to go back to the title of my talk now that you have all the vocabulary you need. So effectiveness of microseismic monitoring, that's basically figuring out whether people are effectively able to use monitoring in determining where to frack. And then for making hydraulic fracturing more efficient, just a better process both on the producer side, the operator side, and one where we're not seeing companies drilling holes in the ground that they don't need to. So that's the title, but I'm claiming you already know what microseismic monitoring is. You might not feel very confident in that because I haven't given you a whole lot of detail, so if you have questions, I have answers. And ultimately, the most important question, though, is what is microseismic monitoring? Answer's still unclear. So I'll give you an image of the tool that's used for microseismic monitoring, basically the way that they collect data, which is a geophone, and that's the center, the yellow thing. The yellow things are put into arrays, so that's what's shown on in this image. Basically, they set up many of them, and they may be under the ground. They may also be above the ground, depending on what sort of measurements you want to take. But you set up geophones and you measure how seismic waves travel through rock. So seismic waves can vary in magnitude, and in this case, they're very low magnitude, and they're caused by the process of fracking. So they're ones that you wouldn't perceive at the surface, but that at depth, you're able to monitor, come up with maps, such as the one shown on the right-hand side, just a general sense of where seismic events are happening, and then therefore able to figure out how fractures are occurring in the rock. So these tools are used they're very similar to seismometers that are used for other earthquakes. So for ones that you can discern at the surface, or when you're studying like the San Andreas Fault, you're also using geophones for that. Now, the purpose of microseismic monitoring, we had reason to believe that it's not always fulfilled. So one of the first conversations that Mike and I had with a geophysicist from the oil and gas industry, he said that there's some tension between those engineers who have their less sophisticated methods and the geophysicists who try to use these very expensive technologies but aren't necessarily successful. And so engineers who are told by geophysicists to drill in this one spot and then it doesn't wind up producing quite as much as they expected it to, aren't very happy with them. So we wanted to see if there was any reason for that, if the data actually show that there's a miscorrelation between what the geophysicists say and what is actually coming out of the ground. So microseismic monitoring is, the whole purpose of using it is to figure out where to drill, figure out how big the reservoirs are, and then to predict how well the wells will perform. But the data are often very difficult to interpret because it's not very clear, the understanding is not very clear of the relationship between how fluids travel through fractures and just how the seismicity leads you to understand that. So it's difficult to interpret, and the data sometimes have a large range of error. So now you know all the background you need. We're going to move on to what my actual research question was and why it matters. And the research question is stated thusly. Does an increased use of microseismic monitoring make hydrocarbon production more successful, specifically in California? And we care about this, if you're not already convinced, because we want oil and gas production to be more efficient, both on the consumer side of things, because that means that our situation is better for prices of products, but also from the producer side of things, where they want to cut costs, they want to be more efficient as well. Microseismic is an expensive technology and one that companies use to make strategic decisions. So if their decisions aren't very informed right now, we want to help to make that better. And now to answer that question. We have two parts. There's the part about the technology, so who's using microseismic and to what extent. And then I'll get to another part later, which is how successful have producers been at getting oil out of the ground, because then we can compare who's using microseismic and who's getting the most oil out of the ground, and are they the same or are they different people? So in order to understand who's using this technology, we ranked the 7 operators in California from high tech to low tech. That means high monitoring tech use and low monitoring tech use. And we based this on a very scientific source of data, Google Scholar, where we Google searched the name of each company and the word microseismic, and sometimes the word California, just to see if there were different search results if we included the word California in our search versus if we just opened it up to how each company is using microseismic throughout the world. And so we figured this was a fair proxy because companies that do more research about microseismic monitoring are using it to a greater extent, and because we couldn't really get quantifiable information otherwise about who's using microseismic more than others, just because of the competitive interests of those companies. So we use the Google Scholar results. This is an example of how we did that. So this is a Google search for Aera Energy in quotes, and then microseismic California. And that came up with 10 results. But we thought, Aera's been here the longest. That's a little interesting that they have the fewest results because maybe they've been experimenting more than these other companies. So we added onto Aera's search results Shell microseismic California and ExxonMobil microseismic California, figuring that since Aera is a subsidiary of those two companies, they would have access to the technologies that those other two, the big super majors, use. So now you can see how that all fell out. Basically, a histogram of the search results for microseismic and tilt meters, the technology I told you about, and now here's the proof that it's not quite as significant. It doesn't represent as much of a chunk of the total search results as microseismic in California. That's why we focused our study on microseismic. The first bar here on my far left is AERA and Shell and ExxonMobil. So they are the highest tech user out of all of these companies, followed by Shell, but that's just to show you where they kind of add into the AERA column. And then the next largest is actually Chevron, which is a pretty small bar in comparison, followed by ExxonMobil and then Occidental. And the three smaller companies, Vintage Production, McPherson, and Brightburn, returned no search results. Brightburn had 3, but that, in the comparison with 4,626, pretty much nothing. So we made we made categories of who the high-tech operators are and who the low-tech operators are. The high-tech highlighted in red because they have the largest bars on this graph, and then the low-tech, you can't even see them because they have so few search results. So this just, again, it tells you the count of the number of search results for each company, and then the name of each company. And if you can't see in the back, AERA remains our highest tech company. And that was what motivated our choice for our case study, which was to look at AERA as the textbook sort of high-tech company, the one with the most search results, the one that's been in California the longest and has been fracking the most. And then compare that to Vintage Production, which has no search results, but they also have been in California for a while, longer than any of the other competitors. So we compared those two companies throughout the rest of our study and then looked on a broader scale at all of the other companies just to see if they confirmed what our case study showed. So that brings me to the next part of the answer, the production success part, where we asked, so who's actually being the most successful in California? Who's growing the fastest and producing the most oil and gas? And our source of that data was the state of California, which again was excellent. They gave us great access to well log information and production volumes, with the unfortunate disadvantage that the production volumes only exist in sum. So what I mean by that is that we can look up the sum of total production for AERA Energy in 2010, but we can't find out exactly how much they're producing out of any given well. We also can't figure out exactly how much they're producing out of just fracked wells. So we had to use a bit of judgment just saying, well, AERA Energy produces or fracks a certain percentage from their total wells. So we mapped out exactly what percentage of their total wells are fracked and what percentage are non-fracked. If it's hard to gauge from the histogram bars, you can look at the pie charts for a general sense of the red sections being fracked wells and the gray sections being unfracked wells. And even further, to quantify it, you can see the percentages numerically here. So by far, the highest percentages for fracking out of total wells are Brightburn operating, but their sample size is 11. So 64% of those 11 wells are fracked. Second is ExxonMobil Corporation, which fracks 62% of their wells out of 197. So a little bit larger sample size. But then out of the biggest sample sizes, we see AERA Energy coming in at 22%. So they definitely frack a significant number of their wells, a significant percentage of their wells. And that tells us that we should see some visual representation of their growth that comes from fracking. When we plot out just how much they're producing every year, we should expect a significant amount of their production to be from fracked wells. And that's exactly what we did. We looked at how much oil on the top, the green curve, and how much natural gas on the red curve they were able to produce each year since back in 1995, which is 6 years before they started fracking. 2001 marks when fracking started and when our data on what percentage of fracked wells out of total wells exist, and then all the way to the present. So you see an interesting phenomenon here, which is that as AERA really steeply ramped up their total number of wells, their production went down very significantly. So the green and the red curve go down, maybe flatline a little bit, but while they increase their number of wells significantly. And that was pretty curious. And we said that can't be, or at least there must be some sort of change still going on behind this data. So that led us to take linear fits of the production volumes and say, let's just see how their rate of growth changed pre-2007, which is when, pre-2008, so 2001 through 2007, when they were fracking, but there weren't other companies in California fracking. And then after 2008, when vintage production started, and then all the other companies started to follow and frack in California. And this is the result from that, which shows us that pre-2007, Aera Energy's rate of decline year over year in production was pretty steep. But then as more companies started to put competitive pressure on Aera, they started to still decrease, but decrease by less. So the slope here is steeper than the slope there, basically. They're not increasing every year in their production, but they're decreasing by less. So they're seeing some sort of improvement. And to quantify that, if you're not convinced by the image, you can see that their oil slope went from negative 749 to a slightly shallower negative 623. And their gas slope went up by a lot more, so negative 408 to negative 43. So some impressive improvements, and we might see that they'll start to increase later on as this competitive pressure starts to grow for them. But for now, we want to compare them as they've worked to Vintage Production, the low-tech company. And we see a very different story here. Vintage Production, in 1995 up until 2008, when they started fracking, had a very jumpy, they continued to have very jumpy production volumes after 2008, but they were declining until about when they started fracking, and then generally increasing after they started fracking. You can sort of see this visually, but I want to give you more of a quantifiable sense of that. So pre-2008, the rate of decline of their oil production was negative 25, and then they very rapidly increased their rate of production of oil to 219. That's positive 219. And their gas slope has the same story, so went from negative 18 to positive 249. So Vintage appears to be more successful than Aera at this point, appears to have grown much faster and fracked better. And we can do a side-by-side comparison in order to think about that more. So on the left-hand side, all the information will be about the high-tech case, Aera. On the right-hand side will be the low-tech case, Vintage. And comparing their oil production, you can see that before 2007 and after 2007, all the information that I already gave you before. And now we're going to take the change in the slope. So basically just do this formula. The change in oil and gas slope equals the post-fracking slope minus the pre-fracking slope. That tells us that between 2007, pre-2007 and post-2007, they increased their slope by 125, and then Vintage increased by 245. So they increased by more. That just sort of corrects for the fact that Aera's production was always negative year over year. And then when we compare their natural gas, we see a somewhat different trend where Aera actually increased their slope by more than Vintage did, so by 364 rather than 223. Now, that does seem a little bit more optimistic for Aera than what we said before, which is that Aera was just declining and declining every single year, and Vintage went from declining to increasing. But the overall takeaway from this is that Vintage has increased their oil and gas production by more than the low-tech case. Now, we want to compare all of the 7 operators just to give you a sense of where they all fall out on a plot between the percentage of their total active wells that are fracked. So back to that histogram you saw where there was a little red bar. It said, here's the number of fracked wells out of all of their wells. So this sort of corrects for any difference between the people who frack more versus less. And then along this axis, you see the slope of oil production after fracking began. So basically, are they increasing their oil production now, or are they decreasing their oil production? And this top area is increasing, this bottom area is decreasing. And then the circle size, the bubble size, represents the number of microseismic search results that we saw for each of these companies. To give you a sense of who the high-tech companies are, those are the big bubbles. Who the low-tech companies are, those are the tiny points, the little bubbles. So Aera being the largest, we see what I just showed you before. They are decreasing every year. They have about 22% total fracked wells, so they fall right here. And the main takeaway from this plot is that the biggest bubbles are not up high. They're down low, which is not what we would want to see as oil and gas companies, at least, who want to optimize their production, who want to get the most oil out of the ground and use technologies that promote that. So there doesn't seem to be a distinct advantage to these companies using microseismic monitoring. And I've sort of spoiled the conclusions already, but I want to really drive them home that the companies that use this technology do not appear to be growing any more quickly. Our data suggests exactly the opposite, and so they might want to reconsider what they're doing, both for the sake of general efficiency and for their profit margin. And our results should help them to make these decisions, to just be better oil and gas companies and be more competitive. And the oil and gas industry overall is a very competitive industry. You saw at the very beginning of my presentation that it's growing very quickly. It's in all of our best interest to try to promote that they're more efficient. And so I hope that you'll take that away from this presentation. Thank you for your time, and I'm open to questions.